We are back today, and I wanted to go through an example problem for writing the diffusion of materials using this using this Kroger-Mink notation and figuring out intrinsic and extrinsic reactions. So, in indium oxide, we could have Schottky or Frankel defects. So, the activation energy, i.e., activation energy is delta HF, is for Schottky defects 2 electron volts, while for both cation and anion Frankel defects is 3 electron volts. So we know we're going to have to, let's kind of continue reading the problem. Often also, indium oxide is doped with UO2. So we want to plot the log of the concentration of host cation vacancies. So which is our host? So our host is what has the intrinsic reaction, so we know it's indium oxide. And then our impurity is UO2. So now, what are we looking for? So we're plotting the log of the concentration of cation vacancies. So a host cation vacancy is just a vacancy in an indium. That's it. So, and then we also want to plot the log of the diffusion of the cation as a function of inverse temperature. So we eventually want to create a plot like this. Actually, let's go ahead and we're going to kind of go through, added quite a few, some distance here. So we want to plot as a function of inverse temperature, so 1 over T, a log of concentration of vacancy in indium, which we know is going to be 1, 2, 3. And then we also want to plot the diffusion of the host cation, which is going to be indium, log as a function of 1 over T. Now, I know I'm going to have, because in that problem statement, I have an intrinsic and an extrinsic reaction. What temperatures, so if my temperature is high, what is 1 over T? Very, very low. At high temperatures, what dominates? So if temperature is high, i.e., this is in these conditions, what dominates? Intrinsic. If temperature is low, for example, then my 1 over T is very, very high. This is where extrinsic dominates. Extrinsic reaction. So I'm going to dominate I here, extrinsic here, I here. That's it. That's what we're kind of what we're dealing with. That's what we're working with. So extrinsic is going to dominate at very, very low temperatures or high 1 over T. So we need to figure out what's the concentration of these indium vacancies. And again, IN2O3, this material is a ionic crystal. So what type of vacancy mechanism dominates in ionically bonded crystals? Well, we know it's what type of diffusion mechanism, it is the vacancy mechanism. So vacancy diffusion mechanism. So that is kind of the key idea. So how do materials diffuse? Via the vacancy mechanism. So we're going to have to go ahead and write these concentrations and figure out where all this, where these materials exist and what the slopes are. So let's go ahead and let's kind of start from the beginning. So let's start with intrinsic first. So intrinsic. So what is my intrinsic reaction? Do I have to worry about the anion Frankel defects? No, I don't have to. I worry about them at all, actually. Why? Because that is not the reaction that's going to dominate. The Schottky defects are going to dominate. How do I know that? Because the delta HF of Schottky is less than the delta HF of my. So I'm going to have more of these Schottky defects. So what is the Schottky defect for indium? So let's go ahead and do null goes to vacancy in indium. We know that's -3 plus vacancy in oxygen. We know that's sp2. Uh-oh. Am I charge balanced? No, I need to do this. I need to do this. Now I'm good to go. Charge, mass balanced. Excellent. What's kind of the next step for our Schottky equation? Well, I could write my K equilibrium, which is the K Schottky, which is the fact that my vacancy in indium. Now, here's the rub. What's the exponent? So hopefully remember back to this goes to C plus D. And now we're going to get our K rem is what? Concentration of products over concentration of reactants. And then C, D, A, B. So with that same expression, if we have that prefactor here, we need to kind of put our concentration, and we need to square it. What about for vacancies of oxygens? We're going to put it cubed. And that is going to equal to exponential minus G formation of Schottky defects over KT. There it is. What is our electroneutrality expression? Well, this one is a little bit trickier. So vacancy in indium. So 1, 2, 3. This is my electroneutrality expression. Does this make sense? What is this saying here? Well, it's saying that the concentration of indium must be, this is kind of, here is our key kind of electroneutrality expression. So let's kind of break it down. So if my concentration of vacancies, let's say I have two, let's say my concentration of indium is equal to 2. So what's the total charge here? So if my vacancy in indium, this is equal to 2, what does this have to be? So my total charge would be minus 6. So let's plug that into this expression here. So now we have 6 divided by 2. That means that my concentration of oxygen is just equal to what? 3. So these are two positives. So if my total charge here now is plus 6. Good to go. One quick trick that will kind of always keep you out of trouble is when you're writing electroneutrality expression, just write the charge of here. So I always put that prefactor here, 2, 2. That'll always kind of work it out. But again, you could just do that. Again, this is just pretty straightforward math. But this is my electroneutrality expression. So that's it. So if I also want to, again, for the intrinsic reaction, if I want to now figure out what is the concentration, if I'm trying to solve for the concentration vacancies in my host, I can now use this expression and plug it back into here. So now I could say that vacancy here squared is equal to 3 over 2 times the vacancy in indium to the, because I'm just plugging in, so I'm moving this over to the cube power, and then that's equal to exponential minus G formation of Schottky over KT. So I'm not really concerned about prefactors. Why is that? Because I'm asking to plot the slope here as a function of temperature. So prefactors I'm not too worried about. So in the end, you'll see that here this scales as what? As exponential minus G formation of Schottky over 5 KT. So my slope for my intrinsic reaction as a function of the concentration of these vacancies is going to be just this minus basically minus G formation of Schottky, actually G formation, excuse me, of Schottky over 5K. That's the value of my slope. What about the diffusion? Well, I can kind of do that now as well. So the diffusion of indium is going to be proportional to the concentration of indium vacancies here times my tau times my r squared times my f divided by 2d. Again, this is just going to be some prefactor. Does it have any temperature related to it? No, it's just a squared. It's going to be equal to 1. D is equal to 3. But what about here? We clearly have a temperature relationship here. And I also remember that this is proportional to exponential minus G migration over K. So what we'll end up with for the diffusion on the intrinsic side is a plot or a function that looks like this. So minus G formation Schottky over 5K minus G migration over K. That's it. That's the value of the slope for diffusivity. Now, let's do the same exact thing, but now for our extrinsic reaction. So I'm going to kind of erase at this point. Hopefully people kind of saw, you could kind of go back slowly through those videos, or this video, and kind of double check your answer. So I'm going to go here. I'm going to do my extrinsic reaction right now. So very, very similar steps. Let's see that a couple little easier flaws. Now, let's do extrinsic. For my extrinsic reaction, again, so what are we doing here? So we're doping indium with our host, indium oxide, with this impurity. So the key thing here, whenever you start these extrinsic reaction, what are we trying to figure out? We are trying to plot the log of the concentration of host cation vacancies. So we need, when we write our reactions, I need to have a reaction where I have basically a vacancy in indium, and it's 3 here. Oops. I have to have this reaction. So if I have this reaction, what else can give me a positive reaction? Well, if I do a substitutional cation where U replaces indium, so I go from 3 plus to 4 plus, that's 1. So I do that by 3. Now I could do the rest of my kind of analysis here. So let's mass balance across here. So I'm going to need to have 3 UO2 plus 6 oxygen X. Good there. Indium, I have 2 here. That's it. So this is my reaction here. Now I could also, I need to kind of go through my steps again. So do I have a relationship with kind of temperature here? Or how can I figure out what is the concentration of my vacancies? So let's go ahead and write down what is going to be our kind of charge. Let's do our electroneutrality. So it's going to be this indium 1, 2, 3, and this is going to be 3 here, and that's going to equal to U indium here. That's it. Again, this is kind of the same same idea as previously. So how do I figure out how the concentration, is there any temperature dependence here? No, I just have my electroneutrality expression because I know that I'm creating these vacancies by basically kicking off, or basically they're created as a function of these cation substitution. So I know that my concentration vacancies in indium is going to be proportional to concentration of U in here over 3. So is there any temperature dependence? No. So in terms of the concentration here, this is just flat, and the value would just be this log of basically the concentration of U indium positive divided by 3. So it would just be a flat slope right here. What about our diffusion for this extrinsic reaction? So let me go ahead and actually erase this here. Let's go ahead and rewrite this. Well, I still have the same, it's still a vacancy mechanism. So my diffusion of indium is going to be proportional to concentration of vacancies times, let's go ahead and go to this value here. So let's go ahead and do here, R squared, your F over 2D. No temperature here, no temperature here, no temperature here, no temperature here. We just have our migration left. That's it. So I could go ahead and I could draw this reaction right here. And so the slope is just going to be this Gm divided by K. Because again, in this proportional to here. That's it. That's how you solve all these problems. So the key thing is, again, writing these relationships and then seeing if you're intrinsic, extrinsic, do you have a relationship with temperature, and how do we go about solving that. So I hope this video was helpful, and then again, I'll be happy to provide more if people still have questions. Thanks. Bye.